super chill, and you're going to notice a theme over and over again. We're going to start that theme in a very chill way today. So let's see. What's a black pen? What's a black pen? Okay. Cool. So today we're starting applications. Most of the applications we're going to do are going to be geometric in here. So the first one is the easiest and most accessible, the area between two curves. You've probably even done some of this in Calc 1. Howdy. Make sure to stop by and get your exam. Oh, it's right there. I got it for you. There you go. So let's say I've got some y equals f of x and some y equals g of x. And I'm interested in finding the area betwixt the two curves. What's that you pointing? What are you pointing at there, Jose? That's
the double helix.
Oh yes, not intended. No goldfish or anything like that intended. Yeah, that is good. Let me make it look less helixy, but it's still pretty helical. Yeah. So that's what I want to talk about today. How do I do this? And what we're going to do is build our formula from scratch. So think in terms. What was that? Are you just saying think in general, or maybe I missed it?
No.
That's okay. I'll just keep going. Think in terms of Riemann sums. When we first got together, the very first day I saw you all, we refreshed our memory about what a Riemann sum was and what an integral was. And we're going to see that multiple times over, because this is how, if you take physics with calculus, this is how the formulas are derived. I don't know what they do in chemistry, quite frankly. I'm completely clueless. I know much more about physics. So let's look at this problem above again. And so this is y equals g of x again, and this is y equals f of x. Step one is I need to figure out where my area starts and ends. So step one is I'm going to need the x-coordinate where we start and the x-coordinate where we end. So right off the bat, we need to solve f of x equals g of x. So we're going to set those two curves equal and find the x values where they output the same y value for x to get endpoints. I'm going to set the general. I'm going to do this in general, and then we'll do a specific example. Just want to get the thing laid out. Yes, sir?
So you're saying f of x is a and g of x is b?
No, I'm saying that this point right here, when x is a, is f of a, but it's also g of a.
Okay.
That the output there is equal. The output is equal in both those locations. Does that make yeah? Okay, cool. Step one, do that. Step two, partition the interval a to b into n pieces. We're heading toward an integral. So what do I mean by that? I mean cut it up into n, not necessarily equal pieces. So to do this, I'm going to pick x spots along the way where I will make my cuts. So I'm going to call this x sub 0 is a, and then x sub 1 will be my first cut. X sub 2, x sub 3, blah, 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 all the way down to x sub n, which is going to be synonymous with with b on the end. So I've got x1, x2, x3. Let's write this up here. So I'm going to say a is equal to x sub 0, the left end point. It's literally the left end point of our interval. And then I'm going to put less than x1, less than x2, less than blah, 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 all the way up to x sub n, which is actually also just the right endpoint. Now let me stop and you tell me if this is making sense. It's very abstract. And I'll never actually ask you to do this process. We're just going to build a formula with this thought process. We're thinking in calculus. Cool. And then the next step is, so what I want to do is make a rectangle above each of those little slices. And I'm going to add up the area of the rectangles to get an approximation. So I need to figure out how high my rectangle would be. And so what I'll do is inside each one of these, I'm going to pick any point I want. So there's x1 star, there's x2 star, here's x3 star. Notice how x1 star looks like it's in the middle, x2 star looks like it's on the right end, x3 star looks like it's on the left end. It's okay, as long as I pick it inside that interval. And it could even be the left endpoint or the right endpoint. So step 3 is in each sub-interval. And we're also kind of building some language and more experience thinking in these sums. In each sub-interval, let's say that's x sub I plus 1, choose a representative point that represents the whole interval. And that's going to be x sub I plus 1 star. Now why do I say that? So let's just look here. In this first interval, this guy right here, where you have x sub 0, and then you have x sub 1, and this was A. I want to pick a point inside there. So I can pick any point I want, but it's going to be my first point. Notice how its index links up with the index of the right endpoint. So in this next interval, where I've got x1, x2, that'll be my second representative. So I've got x2 star in there. And what I'm trying to just emphasize to you is that the index, the subscript on the representative matches the subscript on the right end of the interval. That's all I'm trying to say there, is it? Making some sense? So I could write out the words for it, but that'll just make us all suffer a lot. So I'm going to do that for each of these subintervals. So let me just really quick, in case that, e.g. in the first subinterval, pick x sub 1 star. In this next interval, pick x sub 2 star. And like I said, it could even be one of these endpoints. We want this to be a beautiful general process. So step 4 is using these new representatives. I'm going to go up to the curve. And I'm going to figure out what is the y-coordinate there and what is the y-coordinate there. I'm going to use that as the height of my rectangle, and I'm going to make my rectangle base equal to the subinterval width. So let me show you what I mean with another picture here. So above each subinterval, let's say that it's the, well, we'll draw a picture in a second here. Create a rectangle of height. We're going to have here, it looks like f's on top, f of x sub I star minus g of x sub I star. Let's actually make that plus 1 there. Rectangle of height, that, and width, delta x sub I equals x sub I plus 1 star minus x sub I. Now this is probably all starting to sound like a little bit of mush. So let me draw a picture. Here's top curve. Here's bottom curve. I'm just kind of blowing up on a part. Here's x sub I. Here's x sub I plus 1. Let's make it huge. Inside here, I pick a representative, x sub I plus 1 star. I come up to my curve, right above that, and I draw a line. So this height right here is g at x sub I star, x sub I plus 1 star. And then this height here is f at x sub I plus 1 star. This is the picture I got. And I'm gonna do this on each subinterval. And then I'm gonna make a rectangle as wide as the base using this height right here. So I gotta go through that point. And here's the top of the rectangle. And I seal it up like this. That's supposed to be a perfect rectangle. And that's super blown up so it looks terrible too.
So you use the intervals to make the rectangle.
Yes, sir.
You use the subintervals to plot the dots.
Yeah.
Okay.
Yeah. So I'm using the little cuts that I make as the base of my rectangle. That's how wide my rectangles will be. So if I came over here, Jose, and I did that, I would have a bunch of rectangles that have the width of the base down there, and that kind of approximate the area between those two curves very poorly. So in other words, here's what we're gonna end up with. Let's say I've got this shape here. I'm gonna kind of go through and just do this. And depending on how I situate those rectangles, this picture's gonna look a little bit different. Right? If I use the right endpoints, they're gonna look like this. If I use the left endpoints, they're gonna look like that. And if I use some point in the middle, they might look like that. But I'm gonna put a bunch of rectangles over the area I want as an approximation. Let me stop. I don't know if you even believe me. I'm not sure anybody believes me right now.
No, I'm just.
It's all good. Yeah, let's talk.
So it's just my confusion is like, so the dots that you put on there.
I'm sorry.
So to make like the rectangle, for example.
Oh,
you see
okay,
that
yes.
line that you made in the middle, right?
Yeah.
In the middle. Those dots you plotted from the sub interval.
Yes. Yeah.
Okay,
Yeah.
but the width of the base. How did you determine that?
So, okay, let me give you a
intervals?
specific example. Let's do something very concrete to show you what I'm doing. So let's say I've got these two curves. Let's say I've got y equals, this would be x times 2 minus x. So that's 2, and that's 1. So I got that parabola. And then I'm going to have another parabola, and that parabola is going to just be this guy, kind of the flip of that one. I'm going to make him upside down. So this parabola is y equals x minus 1 quantity squared. And if you plot those out, you'll get those two parabolas. So I want to find this area here. Let's just think about how I could approximate it. So my interval of where these two, where that region is, I got to solve this. So to figure out where this start and end is, let's just go ahead and do it. So I'm going to set x minus 1 squared equal to x times 2 minus x. And then this, I'm going to FOIL that out. This, I'm going to just multiply out. I'm going to move the x squared to this side. I'm going to move the minus 2x to this side. I think that all looks good. So I just kind of moved that stuff over. And now I have to solve it, which is unpleasant. I did not make a nice problem for myself, but I could use the quadratic formula. For 2 times 2, and so that's going to be 4 plus or minus square root of 8 over 4, and that is 2 square root of 2. So the points are going to be 1 plus or minus square root of 2 over 2. So this is the minus one here. So notice you got the 1 in the center, and then it says move over square root of 2 over 2 this way. So there's 1 minus, and then there's 1 plus square root of 2 over 2. So far, so good. Does that make sense?
Yeah.
Okay, now I'm gonna cut this interval. So my interval's kind of weird. But that's the interval where this area occurs. I'm gonna cut that into some pieces. And I'm gonna make my life easy. So the first thing I'm gonna do is say, okay, x0 is this horrible left-hand point, so that's not that easy. But I'm gonna pick some other points in there. So this is like, could somebody on a calculator do this for me really quick? I think it's like 0.3. Could someone check that out for me really quick, please? I think is doing it.
Square root 2 over 2.
Square root 2 over 2 is like 0.707, I think.
0.707, yeah.
Cool, and then if you take 1 minus that, or that minus 1, we'll get like
0.293.
Okay, cool, thank you. So this left end point's roughly this. The right end point is going to be this guy here, whatever the heck that is. So that's going to be like 1.3. Yeah, so that's approximately 1.3. This is approximately 0. Oh no, 1.7, sorry, 1.7. Okay, so now I'm going to cut this thing into some equal pieces. And so I'm just going to pick some nice points in here, like 1/2, 1, and then 3/4. So I've got these intervals now. My new intervals look like this. The leftmost one is 1 minus square root of 2 over 2. And then I've got 1/2. And then I've got 1. And then I've got 1 1/2. And then I've got 1.7, my 1 plus square root of 2 over 2 thing. So these are my new subintervals. And that means above each one of these, I'm going to make a rectangle. And this is, I'm going to approximate that fish shape, that football shape with 1, 2, 3, 4 rectangles. Inside each one of these, I need to pick a representative. So for this first one, so here, this is x0, this is x1, this is x2, x3, x4. Inside here, I'm going to pick x1 star. So x1 star is, let's just pick a number between these two, let's say 0.4. Does that sound okay? And then x2 star, let's just use 1, because I can even use the endpoint. x3 star, let's pick 1 1/4. I'm just trying to emphasize that it doesn't matter where you pick these guys. 1.75, and then x.
That's 25.
I'm sorry, say that again?
For
Thank you, yes sir, thank you. Cool, that didn't look right, that's why I was getting a little distressed there. And then for this last one, we will pick, how about we do 1.6, just to be safe, because that's like 1.7. So I got it in. So now I got my representatives. And that means up here, I just picked these points. So I've got like this point, this point, this point, and then some point over here. Now what I'm going to do is I'm going to go up to the curve, right at those representatives, and make a rectangle whose width is the subinterval that it comes from, and whose height is the function at those representative points. So right there, that one is going to look like that. Then I go over to my next point, which was 1. And I figure out how high was the function at 1. So here's the top, here's the bottom, and it's going to be as wide as that subinterval right there. And then I keep doing that.
I see, yeah.
Does that help a little bit as to what's going on? I think a solid picture definitely helps.
Yeah, it helps.
Okay.
This helps. Yeah.
Cool. Is anybody in any other clarification needed here? Because this is pretty nitty gritty. All right, we're good. So I go through, I'm picking these representatives, and then I'm making rectangles above, and I add up all these areas. So add up the n rectangle areas. And let's see what that's gonna look like. So the first one is gonna be the height of the first one. So that's gonna be f of x1 star. And it looks like I've got f on top. It doesn't always have to be, f could be the thing on the bottom. You'll see what I mean. So I take the height at that first representative times the width of that first interval. So check it out. This is height in first interval, first subinterval. This is the width of the first subinterval. And so right now, I've just got the very first rectangle's area. I'm gonna go through and add these all up. So the next one is gonna look like what? What is it gonna be? Plus sum, or plus f at x2 star minus g at x2 star times the width of that little subinterval. And now I'm just gonna do that all the way to the end. And I have to do this in general because I'm about to make this look really pretty. So that's the approximate area. That formula will change depending on how I made the cuts to make these and how I pick the intervals inside. So at this stage, this answer could vary wildly. But here's what we're gonna do, friends. We're gonna let the number of rectangles become infinite. We're gonna let the width of each rectangle go to 0. And those two things are the same process. So our approximate area with n cuts is, I'm going to use sum notation, summation I equals 1 to n, the height of the first one times the width of, the height of the ith one times the width of the ith one, so that's I down there. And this summation here, that's just this, written in a compact form. There's nothing fancy, this is just this notates into this. Now what we want to do is we're going to take the limit as the number of cuts goes to infinity. And this, if f and g are fine, so if f and g are continuous, that's all we need. They don't have any breaks in them. Where we're interested, this becomes the integral. So when you have this sum, this is a Riemann sum. I showed you this the first day of class, and I'm sure you've forgotten it, but you're going to see it many times over the next couple weeks. This becomes the integral. So integral is just a sum. That's why it looks like an S. It literally is a sum of these quantities, so that just turns into f of x minus g of x dx, and this is the area formula. And I just did all that to build that damn area formula. Now we can use it. You'll never have to build it. I just need you to understand roughly how it got there and use it, so let's use it. I did create a new web work that's very tiny. Yusuke, you'll be very happy. It's very tiny, tiny web work that we'll start on today. Let's do an example together. We're going to be doing volumes and all sorts of really cool stuff with this exact thought process. And every time you see it, I swear to you, it's going to be a little more intelligible. I promise. So, find the bounded area, so notice that's a very important word, between y equals x squared and y equals x cubed. Step one is plot this shit out. Make a graph. If you're trying to find the area between two curves, you want a picture. So I highly recommend you get Desmos out every single time you do this, or you do a by hand plot. Let's say there's y equals x squared. Let me show you something interesting here. When I do y equals x cubed, it looks almost the same. Notice that they both have the point 1, 1 on them. So if I got one here and one here, that's on both curves. And so is 0, 0. Does that make sense that those points are on both curves? When x is 0, y is 0. When x is 1, y is 1. So those are common points. How does x cubed sit compared to this one? Is it above or below?
Has to be to the right. X squared.
Yes, yeah, of the x squared. Yeah, and it is underneath here. Let's think about y. Notice if you take a point 1/2, what's 1/2 squared? Well, that's a quarter. What's 1/2 cubed? It's an eighth. So the cubed graph actually lives under the squared graph in just that region, and then they become flipped because 2 squared is 4, but 2 cubed is 8. So the only place they're equal is at 1 and 0, but otherwise the x cubed is underneath, and you need to know that to do this right. Desmos, right? We get out Desmos. So now I know my top curve and my bottom curve. Let me write this whole formula that I put up here in an easier way for you. So mnemonically, just intuitively, the area is going to equal the integral over the x interval of the top curve minus the bottom curve. Dx. That's the game. So here, we now know that they run from 0 to 1, so I'm going to integrate from 0 to 1. That's the range of my x slices. I'm making slices, and I want to know what range do those slices go from 0 to 1. Does that make sense? Think about the slices we were making. They were vertical slices, and we cut from 0 to 1 to get those little rectangles. You just want to think, what is the range of the rectangles that I'm doing here? The top curve is going to be x squared, the bottom curve is x cubed. In this range, dx, that's it. Now I crank it out. So it's the antiderivative from 0 to 1. That's 1/3 minus a quarter. Put in the 0, you just get 0. And I believe that's just 1/12. So that's the area between these two. Yes, Jose.
How do you decide which one's FX? Yeah.
That's that's why you'll want to plot so you can see which one's on top. Because sometimes it's going to even change. You're going to have two curves where they take turns being on top and bottom, and you got to figure out which one's on top in a given spot.
So whichever one's on top, that's f of x.
Yes, sir. And honestly, this is the way. Think about this. Top minus bottom.
Yeah.
That's the way to go. And then don't worry about who's F and who's, because they might be weird and a problem.
So in this example, the top line is x squared because that's where we did our slices, and like, or sorry, what I'm asking is when we did our slices during that period, x cubed was below.
Yeah, absolutely.
And
Yes, sir.
so the answer will never be negative?
That's good. If you get a negative answer, you probably have the wrong thing on top. You want, because this is an area that we want, and areas are always non-negative. So if you do get a negative, you probably just flipped who was on top and bottom. Kind of a good sanity check.
No, yeah. Okay, that makes sense.
You good? Yeah. Let's do another one together.
I have a question.
Yes, sir.
Where is that the x cube? Like in the
Can you?
like 1/3 minus 1/4.
When you integrate it.
Oh, when I integrated. Yeah, sorry, that should have said x cubed, sorry, I was getting a little excited. So that one went to 1/3 x cubed, that one went to 1/4 x to the 4th, thank you. Did it, my head had it, or didn't have it, yes sir.
So what happened after that? Can you?
Oh, and then,
Oh, you just plug it in?
I just plug in the limits, so I'm just evaluating the integral, really, to get that.
I see.
Does that make sense?
Yeah.
Cool. Good questions, John, thank you. All right, let's do one together. So, you might need Desmos. You might need some Desmos. So for this one, I'm gonna give you the X range. So find the area bounded by, we're gonna do a little bit of practice so that you see every kind of question you might see of this ilk. Find the bounded area between, and what happens is you just get a list of curves. So we've got y equals e to the x, y equals e to the 5x, x equals 0, x equals natural log of 3. Get a picture. Every time you do this, get a picture. So you're gonna wanna get Desmos out. Take some time, make a picture, and let's see if our pictures all agree. And then maybe do a little shading, you know, like what does that area look like? It's gonna help you, and it's gonna get a little fancier on Wednesday, so we kind of want to practice getting this all in gear.
Is that x equals 0?
Yes, sir. Yeah, that is 0. It looks like a 6, but it did mean 0. Let me make that a little better. Natural log of 3. I don't know if you can even do these on Desmos. You might be able to say x equals and see, get a vertical line.
I just put natural log of 3.
Oh, can I see what? Oh, look at that. Oh, dang. That's nice. Yep. So it really, really helps. Because we have the basics. I've forced you to learn the basics about some of these graphs, but there's some subtleties here that we don't know about. So first off, when x is 0, they both go through 0, 1. Right? Are we seeing that? They both go through there. And then they sit like this. Which one's on top? Which one is on top?
Y equals e to the 5x.
E to the 5x is on top, so I'm gonna make this like this. So by the time I get out to natural log of 3, on top I've got the e to the 5x curve, and underneath I've got the e to the x curve. So this is the step 1, is seeing that picture. What am I even doing here? And we're finding the area of that cool little horn or curvy slice there. Does that make sense? So let's do it. Find that area. Let's get it, and if you want, get a decimal approximation at the end. It's our first engineering project. We've got some new ones coming up this week. On the exam, I think you're probably not, just really quick, I forgot what you did. I think you did really well. Yeah, you're fine. Yeah, you don't need to do corrections. But this problem, I didn't grade because that formula wasn't on the sheet. So the formula for this was not on the sheet I gave you guys. And so only Vincent could do it because he had written down the formula. So it was impressive. So if you want, by Friday, when corrections are due, you could do that for extra credit if you want. It's like 10 points extra. If you want, but you don't need to. You know. Yes?
Is this like, is this a reciprocal?
Oh, yeah. I think I can tell everybody. Yeah, so on that last one, the perfect on 3B, Othman's asking about this. To get absolute perfection on that one, you needed to pull these guys together. And I think only one person did that. Who did that? Was that you, Vincent?
No.
Wasn't you? No. Otherwise, it was like half a point. So like when I said simplify completely, I was just like taking off tiny bits. That was all. Your answer's right. It just, yeah.
So, did you get it? Was it this?
Oh, yeah. Yeah, you did, yeah. That was
This
you.
is sorry.
Oh, it's okay, but this part's wrong.
Okay.
Yeah,
This
yeah.
is not the same as.
So there's more to the answer than just this part of your answer is incorrect.
Okay.
The zero part. This first part was okay, but when you put in the one, you don't get 0 and 0. So just check that out.
Okay.
Yeah,
And this
yeah.
is okay?
It is, you don't have a plus C on it, but yes, that is okay. But you'll, check it out. This, one of those two numbers is wrong.
Maybe it's a 1 minus 1. No.
Oh, this,
Something.
yeah, you just check it out. It's a tiny little detail. But you actually got the wrong value. That's why it took off 2 for that. And here's that, remember good old, where I told you that would happen a billion times? It's happening right here. We feel okay about this. Now I can plug those in. I've got 1/5 e to the 5 log 3 minus e to the log 3. And then when I put in the zeros, so that's just putting in the log 3 minus, now put in the 0, get 1/5 minus 1. And we can simplify this. And we're going to, damn it. So this is equal to 1/5 e to the log 3 to the 5th. Because I want to get it into this form so I can undo it. Can't undo it until everything is inside that box. Minus, this is just 3. And then this is gonna be minus 1/5 plus 1. I'm just distributing the minus. So this turns into 3 to the 5th over 5. Minus 3, minus whatever the hell this turns into. That's minus 2, minus 1/2, so minus 11. Or minus 1/5. I think that's your answer. But if you got anywhere, if you got to here, that's brilliant, and I'm happy. You can do it on a calculator if you want. But that's the prettiest answer, I believe. Oh, it's not even the prettiest. I guess 3 to the 5th is 243? Maybe somebody could check me on that. So this is 232/5. There's the best answer. But seriously, if you got here, you're rocking it. Is there any questions on getting to that place? Yes, sir.
How, I mean, when you, if you, like, for exam purposes maybe, and you give us something, and we don't, we can't like put it on Desmo, it's like what? Like, are we gonna have some ridiculous graphs?
Oh, yeah, I mean, if it's something funky, I'll hook you up. I promise. I won't leave you hanging. That one was easy. I got that one handled. Let me give you a new one. This one is very fun, so that might be scary. Do you hear me say that? And y equals x squared plus 4. Step 1, plot them. Step 2, find the intersections. Let's just do that together first. Plot both these curves, they're both parabolas. Figure out where their intersections are, and we'll proceed after that. Or you can just proceed, you can rock it. But step 1 is find the start and end. those two equal. If you're not quite sure what to do, that's what you want to do, set them equal and solve. It should actually turn out really nice. So yeah, kind of to your point, Alexander, like if I had this on an exam, I would give you the graphs of those parabolas, but I wouldn't give you the intersection points. And I would say, find those, you know, yeah. You should get plus or minus 1. And once you have those, you definitely need the picture to know who's on top and who's on bottom, because it's not obvious at all. So I'm gonna have to do a little work here myself. 7, that guy opens downward, and that's 4, that guy opens up. So I think, you tell me, you're gonna have the picture in front of you. Oh, the intersections are plus and minus 1, so we're gonna have to redo. That's 1, that's minus 1. Yes, sir.
I'm just still looking at this one.
Yeah.
So what is that negative parentheses 1 over 5 minus 1?
This here,
Yeah.
this was when I plugged the 0 in. So when I plugged in the 3, I got, you're cool with that, or the natural under 3, sorry. Then I plug in the 0, Jose, and e to the 0 is 1. So that's 1/5, and then minus 1.
Okay.
Is that, and then I'm subtracting off that whole thing, right?
Right.
So I had to put it in parentheses.
Gotcha. Okay.
Sound good?
Yeah. Cool.
Cool. And then make sure you use parentheses when you subtract stuff. That's a really common error. You should get 4. A beautiful 4. And if you didn't, let's talk. Or if you did, you don't know how, let's talk. That can happen too. Let's make sure we're getting 4. Is it okay if I erase this, Jose? Sorry, I just, yeah, cool. let's make sure we're cool on that other one first with the parabolas. But if you want to start on that one, please go for it. Keeping in mind it's going to be a little bit, there's a trick in it. Even though it looks simple. Maybe somebody can tell us what the quirk in it is. Oh, you're okay. You're good. I appreciate how courteous you are. What do these lines look like? These two. What kind of lines are these? Vertical lines, right? Yeah, exactly, yeah. So these are vertical lines. So let's take a look here. So y equals x squared. That guy. Y equals 1. Right? Horizontal. X equals 0, aka the y-axis. And x equals 2. What's this point right here? That 2. What's the x coordinate of where these two intersect? 1, exactly. So to solve that, you could set the curve x squared equal to 1 and figure out where it's equal to 1. It's also equal there at -1. Right, so we definitely need to know where that's at because our interval actually ends way over here. So now look at how the question is phrased. Bounded by. So we want to find, so here's x equals 2 right here. We want to find the region that has each one of these as a boundary in some way. So here's the x equals 0, x squared, and y equals 1, so that chunk, but also this piece here is bounded by those curves. So we're always looking for bounded. Eventually, we can allow infinite areas, infinitely big. But for now, we're always looking for just the finite. You can think of this as finite area. Something you could draw a circle around and get it. So that's the only trick in this whole thing, is that sometimes the top curve flips. So look at what's going on here. Here the top is y equals 1, and the bottom is x squared, but here the top is now the x squared, and the bottom has become y equals 1. That's why having a picture is so essential, because to do this area, I'm going to integrate, so I'm doing my vertical slices, maybe even put slices in there. Right? I'm making my slices run from left to right, so from 0 to 1, the top is 1, and the bottom is x squared. Understanding this is key, because it's going to get a little trickier when we start spinning things in space and making 3D things, and we're definitely freaking doing that. So this is on 0 to 1, that's how it goes. Then over here, from 1 to 2, when I run the slices from 1 to 2, now the top is the x squared, and the bottom is the y equals 1. So this is the top, now that's the bottom on 1 to 2. Does that make sense? Fun? Feel good about that? Okay, cool. And we can work this through. This is wrong, just so you see, it's wrong to say that it's just the integral from 0 to 2 of anything. That can't be, and it's not the other way either. We've got to break it and look at the geometry. So just use your sense about geometry. If you were doing a woodworking project, if you were doing some mechanical work or something, right? You're just like, look at the picture, think about what has to happen, and just remember top minus bottom, bigger minus lesser. Keep things positive. So this turns into x minus a third x cubed from 0 to 1 plus a third x cubed minus x from 1 to 2. Maybe put parentheses to keep yourself safe. Plug in that 1, we get 1 minus a third. Plug in the 0, you get nothing. Plus, now put it over here, I'm going to get 8 thirds minus 2. And then I got to plug in the 1, so I'm going to get 1 third minus 1. Hook it all together. Oh my God, look, there's some stuff that's going to repeat again here. So let's see, what do we got? We've got positive 2 minus 2. So these all cancel. And then I've got minus a third, that's minus 2 thirds. So I've got 8 thirds minus 2 thirds, that's 6 thirds. That is, once again, just 2. That is my perfect area. The whole thing. Anybody get 2? That's okay. It's just like day 1, right? Day 1, first hours, it's early. We're just getting to know our new friend.
When you cross out the -2, what does that cancel again?
So that was canceling out this 1 plus this 1,
Oh,
and that, yeah.
I see.
I think it's right. You know, you guys see me make mistakes on a daily basis. So let me know if something looks fishy. I got one last one for you. I'm not going to help on this one until the end.
Real quick,
Yes, sir.
back to that other one.
Absolutely.
Where you set x squared equal to 1.
Yes.
Is that what gives us the bounds, like the vertical bounds?
Yeah, because I was.
So is that how we know that that dotted one is 1?
Yes.
Okay.
100%. Yeah. Perfect. Well done. So I gave you the area between x squared and x cubed at the beginning. Let's do the area between the square root of x and the cube root of x. The bounded area. Look, I'm not giving you x values, so they better intersect. Find the area of the bounded region. Your turn. Get Desmos out. You're definitely going to need Desmos. So can someone help us out? How do you actually enter these into Desmos?
Power of 1/2, 1/3.
Beautiful. Thanks, Alex.
So you could actually.
Oh, does it take roots?
Well, there's a square root.
Oh.
I don't know how to do cubes.
There
so I-
probably is one, but eventually we got to do calculus anyway, right? So good thinking. Powers.
Okay, am I allowed to look at the bound
Of
on
course.
the graph? Or
Yeah, yeah, absolutely. Grab the bounds off the, and then you can confirm it, right? You can get a good suspicion and then check it. Yeah, because solving the equation you would get is pretty rough,
Oh,
pretty dang rough.
to cube root of, you go to functions.
Oh, yeah, I figured there was something like that.
Go to cube root,
Oh,
you just go to
nice.
functions.
Oh, very nice.
Yeah.
Yeah. Yeah. We should be seeing something like that, right? We're seeing some sideways.
Yeah.
Yeah, okay, cool. let's, just to be clear here, let's just make sure, since we're taking a square root, x has to be non-negative, just to make sure nothing weird's going on with your graphs. Because there is a cube root part that's on this side, but. Yes, sir. Come see, come see.
Well, no, my question is
Oh,
that I
okay.
only have like one bound, right?
Ah,
So
so,
can I bound at zero?
yeah. So just think, where are your slices, right? What is the x range on your slices? You want to start at 0. Okay, perfect. Then you just gotta figure out who's on top.
Right, I know that.
Okay, so hopefully we're seeing that intersection points are 0 and 1. So we know we're gonna have this. We just gotta figure out the order. Which one's on top in that interval?
Well, from 0 to 1, it's x to the 1/3.
I think I agree. It's kind of the flip of what we had with the cubes, right? The cube and the square. Yeah, so just make sure that the x to the 1/3 is on top and you'll be good to go. But let's crank it through because we'll see something really pretty, especially if we remember what the other one was. I'll put it up to help us see the pretty. What was that first area? Was it a 1/6? So what did we get for the first area when we did between x cubed and x squared? I'll do it again. I'm pretty sure it's a 1/6. So here. Oh, it was
Wait,
1/12, wasn't it?
Wait, I thought it was the square root and the cube root.
No, this is from before. This, yeah, here's the problem you're doing.
Oh,
I'm doing like an older
Gotcha.
version. Yeah, sorry.
Yeah.
Yeah, pay no attention to that man on the side of the board. Oh, it was 1/12.
We had 1/12.
Thank
Okay,
you.
now I didn't realize that's what you were asking. I thought you were already asking the answer for this problem.
Oh gosh, yeah. No, sorry, I'm being confused.
That's why I was like non-verbal.
Alright, so let's see what we got here. I think they turn out to be the same. That's what I'm thinking.
Oh, Jesus Christ, sorry.
I think I did that right. Let's see, yeah. Goes to, yeah. No. Oh, duh. Yeah, same thing. So we should get a 12th. Did you get a 12th? Awesome, outstanding. We'll talk about how cool that is in a minute. I'm gonna let everybody get there. No, that's not invertible.
got some confirmations, but only got one solid confirmation so far. You good, Othman?
Yeah.
Okay, awesome. Cool.
So I guess what I wanted to say was that this problem here where we were finding the area between x cubed and x squared, these are just the inverses of those functions. The inverse of x cubed is x to the 1/3, the inverse of x squared is x to the 1/2. The relationship between a function's graph and its inverse graph is you flip it over the diagonal. So all we've done here is take that first area that we found, which was 1/12, and literally just flip it over the diagonal. Look, it's exactly the same dang thing. Where the heck is it? It's gone. I don't even have it up here, do I? I think I had it. So we had this one, that's the cubed, and then there's the squared. And they change roles. The x to the 1/2 is on the bottom, the x to the 1/3 is on the top. But they're just the flipped versions of those two that we had over there. So this was x cubed and this was x squared, like that. So I'm just saying the area, this little crescent, is the same crescent, just flipped over y equals x. It should have the same area. It's kind of cool, thinking about the geometry of it all. So this is the task at hand. This is what we got going on. Do we feel like we can do this?
Yeah.
Yeah?
As long as you don't use simple.
It's not too bad, right? Like, given what's been, this is chill. Just set it up, do calculus. You're gonna find over the next couple of weeks that the hardest part is setting up the problems, because what we're gonna start doing on Wednesday is taking shapes like this, and spinning them around axes to create volumes, and then finding the resulting volumes. So if I took this thing, just a little foreshadowing, and I spun it around the x-axis, I would get a really weird looking little horn that kind of looks like this. It has a thick wall, can't really see it. So visualizing 3D stuff's gonna be super helpful if you can do that well. And if not, you're gonna develop some skills. What does this look like if I spin it around the y-axis? So this is the x-axis. What happens if I spin it around the vertical? Yeah, a little bowl, right? Looks like a little cup. So if you spin it around this way, you're gonna get a cup that looks like this, and it's got kind of a thick wall that gets super thin at the bottom. Like, this is the kind of crappy pottery I used to make. Way too thin at the bottom, and it breaks open in the kiln. Anybody ever made pottery?
I have.
You know what I'm talking about?
I do know.
You get that bottom too thin, it just cracks, yeah. Then we're gonna spin them around other lines and all sorts of stuff like that. We're gonna create crazy shapes. Then we're going to learn how to do integrals over infinitely large intervals. So one of the cool parts of this class is you get to see this thing called Gabriel's horn. We don't have any Gabriels in there. And I'm going to prove to you something. We're going to make a horn that looks like this, and it's infinitely deep. So that just goes on forever. That never ends.
Or does it?
It never ends. Yeah, it doesn't end. So imagine it never ends, goes on forever and ever. We're going to build this horn that has infinite surface area, but finite volume. So in other words, you can fill it with paint, but you could never paint the outside with the amount of paint that's inside. So maybe, we'll create this thing. It'll hold like a gallon of paint, but it has infinite surface area on the outside, so you could never actually paint it with the paint that's inside of it. Crazy shit. But that's a couple weeks out. Anyway, I'm either grateful I told you that or sorry, depending on the way your face looks right now. we'll all get there together. We'll all go hand in hand. It'll be great and safe. Alrighty, friends, so what do we got? We got something to do on Friday. We got corrections on Friday if you're turning those in. If you want the bonus, do problem 1, write that up nice, turn that in. So that's also subject to the handout. Look at the guidelines for corrections. Just make them pretty, that's all I want. Yes, sir.
What's the lab work due?
Probably Sunday. It's very short, and we can take some time on Wednesday to work on it too.
Well, no, I was just asking because I like actually want to like get this
Awesome.
like down. So
Awesome.
if it was like due on Friday, I probably wouldn't have work with it.
Do you like the Sunday deadline? Okay, cool. I was like, I could move it to Friday if that would help.
No.
Okay, you don't want that. Okay, I understand now. Cool.
Yeah, usually Saturdays are my calendar.
That's your calc day?
Yeah.
Cool. You're gonna have time, but maybe take a look at a few of them just between now and Friday.
Oh, no, yeah.
Okay, you're not gonna wait till Saturday to surprise yourself. Okay, good. All right, thanks, friends. Good stuff. Thank you. If you got a really good grade, please don't turn in corrections. Just settle down.